Hi class, Module 9, Lesson 2. We will discuss the linear model and also briefly mention testing for pairwise differences. Okay, in the first lesson of this module, we discussed the one-way ANOVA. So much fun. And in particular, we use the R function given here. So you notice this inside function, LM parentheses. This stands for linear model. This is what we're going to get into this lesson. Okay, the basic form of a linear model is like this. Capital YI is xi beta plus epsilon I for I from 1 to n, where this yi is an observable variable, xi is a fixed known variable, this beta is an unknown parameter, and then epsilon I is from the normal distribution, mean zero, standard deviation sigma. We discussed this last time. This is typically thought of as random noise. This unknown parameter, beta, is the focus of statistical inference. Okay. I mentioned this is the most basic form. So in general, we often need the x sub I to be a vector. And I have a vector of length k here. And then we have k unknown parameters, beta 1 through beta k. The general form of this linear model, well, it looks like this. There's a lot of indices, but how does this relate to this basic form? You see here, xi and beta are just multiplied. In the general form, you see you could write beta as a vector, beta 1, out to beta k. And then this part is just the dot product of vector xi with beta. All right. Now, linear regression is the most often used linear model, and I have this as coming soon. Fantastic. This will be in the next module. But today we're going to look at the ANOVA and how it can be written as a linear model. Well, let's remind ourselves from the last lesson. In the ANOVA, we had G groups. This was our one-way ANOVA from lesson 1. And then group J had n sub j observations, or random sample of size n sub j made up group J. All right, so then we had this Yij. This was the mean of group J plus this epsilon ij. Once again, this was our random noise. We had a total of capital N, which is the sum, N1 plus N2 plus N sub G. Now, what we can do is reorganize. We have a total of capital N observations. We can reorganize the capital N Y variables into a vector, Y1 through Y capital N. And we'll have a corresponding group indicator vector, where this is just the group of Y1, this is the group of Y2, out to, this is the group of Yn. Now, this is how we were presented with our small artificial data set of last time. So last time we saw this example, and I will look at it some more today. But you see here are the groups. 2, 3, 1 came from group 1, and then 3, 2, 4 came from group 2, and then 2, 0, 1 came from group 3. 9 observations in total. Wonderful. Okay, so to set up the linear model, we turn this group indicator vector into G variables. I'm really thinking about this as vector valued. And I'll show you this example in just a moment. We have x1 through xg. Each variable, vector valued, is an indicator for each group. And that's exactly what this says here. So the G groups are the second index. What this says is it's 0 or 1. You might have seen an indicator function before in mathematics. It's 0 if the group for observation I is not equal to j, and it's 1 if the group for observation I equals j. Like this. So let me show you, maybe I'll make this slightly smaller. Let me show you what this looks like for our small artificial data set. Okay, in our example, I've just created these 3 vectors, x1, x2, and x3, and then I've printed out y, the corresponding group, and then the 3 vectors. So you can see here, this first vector, you see it's an indicator function. It's 1 when y is in group 1, and it's 0 if y is not in group 1. And then the second is 1 when y is in group 2, and 0 if y is not in group 2. And the third is 1 when y is in group 3, and 0 when y is not in group 3. These are the G vector-valued group indicator variables here. The ANOVA becomes a linear model using these xij's, where capital YI is the sum. Now, here the I goes from 1 to capital N, all capital N observations, and then the J's range over the groups. Let's stare at this part for a moment to make some sense of this. Okay. Each capital Y is in one group. Okay, so only one of these xij's is 1, and the rest are all 0. Okay. So for any given capital Y, well, we have 1 mu here. Like this, where the mu sub j, it comes from the group that yi is in. So it's exactly, back it up one, exactly this, okay? It's just thinking about this in terms of a linear model. Written this way, my null hypothesis that all of the group means are equal becomes, well, look here. My beta j's are the group means. So the null hypothesis becomes that beta 1 equals beta 2 equals out to beta g. Here, these parameters are the group means. So we have the ANOVA model represented as a linear model right here. However, a more common form of a linear model has first variable xi1, always 1, so that yi is written like this. Here, beta 1 is called the intercept term. As a note, the default option in R assumes an intercept term. So let's discuss how to realize the ANOVA in this form. Okay, well, we let beta 1 be the first group mean, but then beta j, maybe I should highlight this one, is the jth group mean minus the first group mean for j from 2 to g. We still have this xij, but it starts at j equals 2 because xi1 is always 1. And then we can write yi like this. So here the I goes from 1 to this capital N. Now in this case, the null hypothesis is written a little bit differently. Okay, so all group means are equal. Well, what that would say would be that all these group means equal the first, in particular, beta 2. beta 3, beta 4, beta 5, out to beta g are all 0. So this is the equivalent null hypothesis with an intercept term. Okay, so beta 2 equals beta 3 equals all the way out to beta g equals 0. Now, as a remark, and I think I will switch to R to show you this, we created these variables, xij, at least in this example, just with a few lines in R. But we could use the model matrix to create them in general. There's two different commands here because we have two different forms of a linear model. The -1, this is no intercept term. And without the -1, well, this is default. This is with the intercept. So let me just switch to R to show you these two commands briefly. This is the example that we've been working with. And then if we ask for this model matrix with no intercept, this was what we saw before. We had x1, x2, x3. You see, these are these indicator vector valued variables where we get 1 if yi is in that group and 0 otherwise. Now, we ask the same thing without the intercept. Here you see this xi1, the first one, it's always 1. And then starting at 2 out to g, which here I have g equals 3 groups, we have this indicator function. Next, I want to talk about linear model fitting in R. So we can use these two commands depending on which version of the linear model we want. This -1, as before, is with no intercept. And this is the default. This would be with the intercept. And here's just this example. I first show without the intercept. There is more output to this summary than what I'm showing, but what I'm trying to focus on is right here. This part, you see, we have this coefficients table that I would like to mention. In this table, without the intercept, these point estimates for the beta j's, we are getting estimates for mu sub j, which is the beta sub j. Okay, so this first estimate, well, it's the sample mean, 2. The second estimate, it's the sample mean, 3. And finally, the third estimate for the third group mean is 1. We could read this off the table. So we are looking in this column. Okay, however, if you look at the same summary with intercept, once again, I really want to focus on this coefficients table in the output. And you look here, these are the estimates for beta j. However, beta 1 we know is mu1. Beta 2 is mu2 minus mu1. Beta 3 is mu3 minus mu1. So if we wanted an estimate for mu1, we just look here, 2. But if you want an estimate for mu2, you have to take what we see in the chart, the estimate for mu2 minus mu1 plus the estimate for mu1. And you notice we get 1 plus 2 equals 3. Back it up 1. You see it agrees with the other table. And similarly, we can do mu3. If you wanted this point estimate for the third group mean, you would take the estimate given in your table for beta 3 and then add the estimate in your table for beta 1. So you get -1 plus 2 equals 1. Okay. Wonderful. Just like we got in the last table. So some remarks here. The two linear models for the ANOVA are equivalent to each other. However, the R commands, which would be this one without the intercept, this one is the default with the intercept. This is the one of the last lesson. They produce different ANOVA tables. So without the intercept, it is testing if all group means are 0. Usually that's not what we're interested in. We're interested, are all group means the same? And that's what comes here. So in this default, which is the one that we used in the last lesson, this ANOVA table tests if all group means are equal, which may be non-zero. This is really what we're interested in with our null hypothesis for the one-way ANOVA. Let's see, let's go back to R, and I can just show you these two for this small example. The ANOVA table that I had printed in the last notes is here. In fact, this example is small enough. There's only 9 observations. You would calculate all these numbers. Okay. Now, if we ask the ANOVA without the intercept, we get a different table. And you notice even the degrees of freedom here doesn't match what we expect, given that we have 3 groups. We would have G-1, which is 2 degrees of freedom. So when we are testing if all the group means are equal and using a one-way ANOVA, as we discussed in the last lesson, without a doubt, we want this default ANOVA table with the intercept term. Okay. The last thing I will just briefly mention, and then you can practice this in our Canvas course, is regarding determining which groups differ. So when we reject H0 in an ANOVA test, we conclude there are at least 2 groups with different means. Another way to say that is there are differences among the group means. All you can really say from a statistically significant ANOVA is that it is not the case that all group means are the same. However, we typically want to know which group means are different. The sum of squares between does not tell us this. Okay, in the table produced by this R command, this gives some information on pairwise group mean differences. Oh, where I have misspelled the word group. So let me wipe this out. But this table does not give all information we want. Therefore, we can use another function in R. We can use pairwise.t.test. This will conduct tests for comparison between all pairs of groups. Some remarks on this. Well, the adjusted p-values in the pairwise comparison of t-tests are what's listed in the table. The default method of adjusting for multiple testing is a home, which controls family-wise error rate. It's an improvement on the Bonferroni for the ANOVA, but you can also use this option to have a Benjamini-Hochberg. If you have a lot of groups, this would be ideal. We know the Benjamini-Hochberg is a better adjustment when you have a lot of hypotheses that you are testing. So I have this function built into our Canvas course with some examples that you can practice. At this point, this is all I'm going to talk about in this lesson. Thank you so much, class.